9.9 part 2. We're going to look at a power series where we're going to take the derivative and we're going to integrate it. So my theorems, such a jerk. Where the hell is it? All right, 9.9 part 2. Our theorem says that if we have a power series and has a radius of convergence where r is greater than 0, then the function f is defined by, if you will, a polynomial function. All right, where x will be the binomial x minus a. Of course, we're centered around a, and a could be a 0, so then it's just x. But it's technically a polynomial function. Here is our summation for our power series. So we can take the derivative of this function, and we can take the derivative of our summation notation. The only thing you got to check for is your constant. So since n is equal to 0, you put in a 0 for the n. That cancels this out to a 1. So that's your c sub 0. Now remember, if you take the derivative of a constant, then that becomes 0. And then your second term, c sub 1 times the binomial x minus a. If we take the derivative of this, the x part becomes 1 times your coefficient. Chain rule, take the derivative of the inside. That's just going to be 1. So this is c sub 1. So technically we lost a term because my series had a constant in it. So you have to check that when you do these problems. If I start with the x term right away, I don't have to worry about taking the derivative of a constant. And what happens is in the derivative of our summation, notice that our n equals 0 now starts at n equals 1, because when n is 1, c sub 1 times a 1, x minus a to the 1 minus 1 would be a 0, giving us that c sub 1 term right there. And all we did is we just took the derivative of the summation. Take the n, multiply it to the coefficient, subtract 1, n minus 1, and don't forget it doesn't show up here, but this is a chain rule. The derivative of x minus a is just 1, so there's no other change. Now when we look to take the derivative of this, the integration of this function, c sub 0, our constant, gets multiplied by an x. So that's our binomial x minus a, plus c sub 1, x minus a, the 1 goes to, add a 1 to it by the power rule, makes it a 2, all over 2. The squared becomes cubed divided by 3. And then you have to have your constant capital C here, so that will stay outside, and our summation still starts at 0. To get this next term, we just move the constant out front because it's not part of our summation. All right, the radii of convergence of the power series for both the derivative and the integration are both still capital R. So although the r stays the same, when you differentiate or integrate, your interval of convergence may differ at the endpoints only. So again, we have to look at that. All right, so example time. For f of x, find the interval of convergence for f of x and f prime of x. F of x is equal to the summation n equals 1 to infinity. Okay, notice we're not starting at 0. So here I want to put in a 1 into my n, so this will be a positive, this will be 2, and x minus 1 to the n plus 1, we're starting off with an x minus 1 to the second power. We're not starting out with a constant, so when we take the derivative of this, We will not have to change the 1 to a 0. All right. So use our ratio test. Add, we got to find the n plus 1 term, so we add 1 to all of our n's, which makes this negative 1 to the n plus 2 times x minus 1 to the n plus 2 all over n plus 2. Divide it by our sequence function, or in this case, multiply by its reciprocal. N plus 1 on the top, negative 1 to the n plus 1 power, x minus 1 to the n plus 1 power in my absolute value bars. And we'll take the limit as n approaches infinity. So let's do some cancellation here. Let's break down the x minus 1 to the n plus 2 as x minus 1 to the n plus 1. We're going to take out one of those bases. That way x minus 1 to the n plus 1 can cancel with this x minus 1 to the n plus 1, leaving you just with an x minus 1 on the top. And we can do the same theory with our negative 1. Negative 1 to the n plus 1 times an additional negative 1. The negative 1 to the n plus 1's cancel, so we're left with a negative 1 on top. So now it's the limit of the absolute value of negative 1 times the binomial x minus 1 times the binomial n plus 1 all over n plus 2. Well, since we're taking the absolute value, the negative 1 is going to cancel out to be a positive 1, so that's gone. We're going to group the n's together and take the limit as n approaches infinity. This will be a 1. 1 times our x minus 1 is the absolute value of x minus 1. So this will converge as long as this absolute value of x minus 1 is less than 1. So if we drop the absolute value bars, negative 1 is less than x minus 1 is less than 1. So 1 is our capital R, our radius of convergence. Add 1 to everything. 0 to 2 is my interval of convergence. Now, we have to test our endpoints. If I test my endpoints, x equals 0, put 0 in for x. Right there is going to give me a negative 1 to the n plus 1 power. So I have two of these. So here, multiply like bases, add the exponents. N plus n is 2n, 1 plus 1 is 2. This is important to look at real close, because now when n is an integer multiplied by a 2, it's always going to be even. You add 2 to every even number, it's still even, so this negative 1 becomes a positive 1. Well, wait a minute, this compares to 1 over n, our p-series, or harmonic series, which is divergent. So because our power on our n is 1, that means it's going to diverge. So if we do a limit comparison test, take the limit at n approaches infinity of our sequence function, 1 over n plus 1, divided by what we compared it to, 1 over n, or multiply by n over 1, you're going to get n over n plus 1, which has a limit of 1, which is true. That's greater than 0, so therefore that verifies that the original 1 over n plus 1 is going to diverge as well. So that endpoint stays open. We test x equals 2. We put 2 in for x. 2 minus 1 is 1, so 1 to the n plus 1. Always a 1, cancel it out. Negative 1 to the n plus 1, this sign will now alternate still. So we need our alternating series test. So number 1 is the limit as n approaches infinity of our a sub 1, or excuse me, a sub n function without the sign, negative sign on it, so the absolute value of that is going to equal 0. As n approaches infinity, it's getting bigger on the bottom, so it's approaching 0. Check. Is it decreasing? Is a sub n plus 1 less than a sub n? Add 1 to the n plus 1 makes it n plus 2. Multiply n plus 1 to the top here, n plus 2 to the top here. Subtract n's, you get 1 is less than or equal to 2. That's true. This converges by the alternating series test. So that puts a, whoops, come back here, I'm not done with you, puts a bracket around the 2 on our endpoint for the interval of convergence for f of x. All right, so since our interval of convergence is 0 to 2 for f of x, what happens when we take the derivative? Well, the radius stays the same, but you may have different, or your endpoints may different. Instead of converging, they may diverge. So we're going to take the derivative of this function. So n plus 1 moves down to the front, there it is, times x minus 1, subtract 1 from the power is n, over n plus 1, and then the derivative chain rule, x minus 1, the derivative of x is 1. That's what this is for. Now remember, we didn't change this to a 0 because we mentioned that when n is equal to 1, this is going to be x minus 1 to the second power. So when we take the derivative of that, we still have an x left over. So we don't have a constant that we lost. So it stays as n equals 1. That's why you got to check those first couple terms. Well, by putting the n plus 1 in front of the x minus 1 to the nth power, those two get to cancel. So that simplifies now to negative 1 to the n plus 1 times x minus 1 to the nth power. All right, test the endpoint, 0. So 0 minus 1 is negative 1 to the nth power. Well, negative 1 to the n plus 1 times negative 1 to the nth, same basis, add exponents, 2n plus 1. That's where this power changes. All right, so this is going to diverge because this is always going to be odd. So if this is odd, this is negative 1 all the time. That diverges. Negative 1 plus negative 1 plus negative 1 plus negative 1 plus negative 1. It's going to go to negative infinity. Let's test that endpoint of 2. Put 2 up here. 2 minus 1 is 1. So that's 1 to the n. So again, that's just going to be 1. You can get rid of it. Now we have negative 1 to the n plus 1 power. This is going to alternate back and forth. Positive 1, negative 1, positive 1, negative 1. So that's oscillating. So this 2 diverges. So my derivative, both endpoints are now open. Okay, example 5. Example 5. Find a power series for 1 over 1 minus x squared and its radius of convergence. All right, so we need to make this look like 1 over 1 minus x, or my a over 1 minus r. And we know that if we take 1 over 1 minus x, this is basically n equals 0 to infinity of our summation of x to the nth power, and capital R is equal to 1. So what I want to do is I want to take the derivative of this right here. Okay, well, think of this as u. All right, u sub. That's going to be u to the negative 1 power. And then you take the derivative of that. That's going to make it u to the negative 2 power, with a negative 1 being multiplied to the front, and taking the derivative of negative x, chain rule. So negative 1, that's what moves out front. 1 minus x is now to the negative 2 power. You subtracted 1 from it. And then the derivative of the inside is this negative 1 right here. Well, negative 1 times negative 1 cancels. Hey, how about that? 1 over 1 minus x, that quantity squared. All right, so we can take the derivative of both sides to find the power series. So the derivative of 1 over 1 minus x is equal to the derivative of the infinity and to the summation of n equals 0 to infinity of x to the nth power, which is taking the derivative of x to the nth. This is going to give me 1 over 1 minus x to the power of 2. We already showed that here. Come back here, it wasn't done. And again, check out that first term. N equals 0, x to the 0 power is a 1. So when we take the derivative of that 1, we lose a constant. So now we have to change our n equals 0 to a 1. And the derivative of x to the n is n times x to the n minus 1. And our radius is still a 1. Because we said when you take the derivative or you integrate, your radius stays the same.